this is the video in AP Calculus over integrals as a net change of a quantity. This is section 7.1 in your textbook. So we're going to look at basically just some applications of what integrals can tell us about different things. So we're going to start here with a particle motion problem. We've got an object that's moving along a horizontal line, and we're given the position function. This is something we could have done back during derivatives. We've been given the position function on a closed interval from -2 to 2. So A wants us to find the displacement over the interval from -2 to 2. So again, this is something we would have done back in first semester. So displacement is just where are you at the end compared to where you started. So we would need to figure out our position at the beginning of the interval and our position at the end of the interval. So we would simply substitute our 2 times into the position function. X of -2 would come out to be -27. And then X of +2 would come out to be 5. So your displacement, end minus beginning, is a total of 32 units. All right. So then B wants to know the distance traveled over the interval from -2 to 2. So when we're looking at distance traveled, we have to actually pay attention to when the particle changes direction. So that's where we would have to take our derivative, or our velocity function, and set it equal to 0. So we would have to take the derivative of our position function and then set it equal to 0. So doing that, we would then factor 6t out of there. And so we have possible changes in direction at t equals 0 and t equals 1. So then we would find our position at the beginning of the interval, and then every time that it could potentially change direction, all the way through to the end of the interval. So I already know that x of -2 is -27. And x of +2 is 5, because I found that back in part A. If I substitute 0 into my original function, then I come up with a position of 1. And if I substitute 1 into my position function, I come up with a position of 0. So then we have to find the displacements for each of these intervals. So to go from -27 to +1 is a total of 28 units. To go from 1 to 0 is a displacement of -1, but the distance traveled is +1. And then to go from 0 to 5 is 5 units. Add those all together. So the distance traveled is a total of 34 units. So again, all of that, you could have been answering this for quite a while. We did this way back in the beginning of derivatives even. So we've been doing problems like this for a good while. So now what if the information had been presented differently? What if we had been given the velocity function to start with? Well, if we were given the velocity function and asked to find the displacement, you probably know this from physics, is just the area under the velocity graph. So for displacement, we could go straight from beginning to end, integrating the velocity function. So if we go backwards from that, 6t squared is the derivative of, it would be t cubed, and if we do old coefficient divided by new exponent, that would be a 2 there. T comes from t squared, old coefficient divided by new exponent would be a 3 with our 2 boundaries. So we substitute the upper boundary in first, and then we subtract from that the lower limit. So that becomes 16 minus 12 minus -16 minus 12. So 16 minus 12 is 4, minus -28. 4 plus 28 is 32 units. And if you look at part A from the first example, our displacement was 32 units. Now, if they want us to do distance traveled, though, just like when we're doing it with derivatives, we have to think about when does the particle change direction. So that, again, is going to be wherever the velocity equals 0. which we already know is at t equals 0 and t equals 1. So here we have the graph of the velocity function. Notice that from 0 to 1, let me get a different color, this graph from here to here, the graph is below the x-axis, so it would have a negative integral value, but distance is not directional, so that needs to become a positive amount. So if we were having to do this by hand, we would integrate from the beginning to the first time that we change directions. Then when we go to add the next amount is going to come out to be negative. We can tell that from the graph. So what we would want to do is we would want to take the absolute value of it. And then the third amount is above the x-axis. So we do not need to absolute value it. Now you may be asking, well, what if I don't have the graph? How do I know when I need to absolute value it? Well, you still know that you need to chop it up based on when the velocity is equal to 0. So you would know you need to integrate from -2 to 0, and then from 0 to 1, and then from 1 to 2. So all you do is you just find those three things, and if one of them comes out to be negative, well, that's how you know that then you need to make it become positive. Okay? So you could work all of this out by hand, just like how we did the displacement up above. I will tell you, though, that when you integrate that, this piece comes out to be 28. This comes out to be the absolute value of -1. And this comes out to be 5. So we come up with a total of 34 units, which, again, if you look at example 1, part B, that was our distance traveled, was 34 units. So the answers came out to be the exact same thing. It's just the way that we went about it was a little bit differently because we were presented with the velocity function rather than the position function. So I've been saying pretty much all year that particle motion or any type of position velocity acceleration problems are extremely popular. So we're going to look at another one, but this time the information is presented differently. In the last one we were given equations for the velocity. Here we're given the graph of a velocity curve. And since it's a smooth curve like this, it's not necessarily geometric where we could calculate the area ourselves. So they've actually given us the areas from 0 to 2 is 24, and then from 2 to 4, you can see that it's 8 there. So based on this velocity graph then, the first thing they want me to find again is the displacement over 0 to 4. So displacement, remember, is directional. So it would be the integral from 0 to 2 of our velocity function, because that's one amount, and then the integral from 2 to 4 of our velocity function. So the area from 0 to 2 is 24 units, and the area from 2 to 4, it's 8, but it's below the x-axis. So the displacement would be -8 there. So that tells us that our displacement is a total of 16 units. So what would we do differently then if it was distance traveled here for part B? Well, for distance traveled, we're still going to go from 0 to 2. And from 2 to 4, the only difference is that since we know that 2 to 4 is a negative displacement, we would need to take the absolute value of that to find the distance traveled. So the distance traveled would be 32 units. I love those kind of problems because they're quick and easy, especially when the area is already given to you right there on the picture. It's just a matter of making sense of the information that's given to you. All right, so here's another motion problem. We are given the velocity function, and this time we've got 4 different questions that they're asking us. The first question is, for what values of t from 0 to 5 inclusively is the particle moving upward? So upward is a positive direction. We move in a positive direction whenever the velocity is positive. So we're looking for where is v of t greater than 0. So again, we've done problems like this. So we would take our velocity function, first figure out when it equals 0. Well, before I factor, I notice everything can be divided by 3. And so then that factors to t minus 3, t minus 1. So these 2 times, that's not when the object's moving upward. Those are the times when the object is stopped. So then I have to create a sign line. Now this sign line, since it's a closed interval, it starts at 0 and ends at 5. And then I've got 1 and 3 on there as the times that my velocity function is equal to 0. So this is a lot like our graph problems we did. Now we're going to check a number in each section. So the first one we could do 1/2. So you would substitute that into your velocity function. And you get 3/4 minus 6 plus 9. That's going to end up becoming a positive number. Then we could check v of 2. That's going to be 12 minus 24 is negative 12 plus 9 is going to be a negative number. And then we could check v of 4. So we've got 48 minus 48 is 0 plus 9 is going to give us a positive number. So it's going to be moving upward in those intervals where I put plus signs. So on the intervals from 0 to 1 and from 3 to 5. If they had asked us for when is it moving downward, then our answer would be from 1 to 3. All right, then B wants an expression for the acceleration. So hopefully you remember that acceleration is the derivative of velocity. So all we have to do to come up with an expression for acceleration is take the derivative of the velocity function that we were given, and boom, we're done. 6t minus 12. Now for part C, they want an expression for the position. So position is going to be the integral of velocity. So they want us to call position y of t. So it's going to be the integral of the velocity function. So that means that we are going to integrate 3t squared minus 12t plus 9. So that becomes t cubed minus 6t squared plus 9t. And we actually should put a plus c on there because it's an indefinite integral. Now, if they had given us a position at any particular time, which they did not, then we could solve for c. But since they didn't, then that's our position function right there. All right, so then D, I have to put it on a different sheet. For t is greater than 0, find the position of the particle the first time the velocity of the particle is 0. So if you go back and you look at part A, we figured out that the first time the velocity is 0 would be at t equals 1. So D is just wanting us to find the position at that time, so at time 1. So you're going to take the number 1 and substitute it into the position function that we came up with in part C. So that works out to be 1 minus 6 plus 9 plus c, so that's 5 plus 4 is 14 plus c. So that's actually the best you can give. You can say 14 plus c. Now c is actually going to be the initial position. So you could say 14 units above the starting point if you wanted to. If you wanted to be more specific as to what that 14 really represents there. All right, so we're going to stop this video here, and I'm going to make a second video for examples 5 and